Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to use the product rule. To get us started, we're going to take a look at the steps involved in applying the product rule. Okay, so let's write it down, the product rule steps. Okay, so the first step in using the product rule involves attempting to avoid using the product rule. Okay, so certain problems are presented in a way where you think you have to use the product rule, but in some cases you do not actually have to use the product rule. Okay, so step one, when you're given a problem where you want to differentiate and you think you have to use the product rule, what you want to do first is try to rewrite the problem to avoid using the product rule. Okay, you want to avoid using the product rule and also the quotient rule also. Okay, those rules are time consuming, and if you can avoid using them, it's highly recommended to do so. Alright, so let's consider an example. So let's say you're given a problem like this. You have y equals e to the x times 1 plus x over e to the x, and you're asked to find dy dx. Okay, so the first instinct will be to use the product rule here, since you have a product of two functions. And in the process of using the product rule, you also have to use the quotient rule and looking for the derivative of this quotient right here. So you have to use the product rule and the quotient rule. But if you try to rewrite this function in order to try to avoid using the product or quotient rule, then you see that it's not that complicated. Okay, so in this case, we can distribute. Sometimes you just have to decompose the fraction or use the properties of exponents by reciprocating. So any kind of rewriting algebraic procedure that helps you execute the derivative by term differentiation, that will be highly preferred. Okay, so in this case, if I just simply distribute e to the x first before differentiating, I'll have y equals e to the x plus, that cancels out, x. And then the derivative is simply going to be e to the x plus 1. So just by rewriting to avoid using the product rule, we have been able to simply considerably simplify the problem. Okay, so when using the product rule, try to avoid using it if possible. That's step number one. Now, in certain cases, you cannot avoid using the product rule. So in that case, what you're going to do, if it can be avoided, you label the functions. Label the functions. You label them u and v. The order is important. Okay? The first one is u and the second one is v. It's not that significant for the product rule, but when we get to the quotient rule, it's extremely important. So you want to start labeling them correctly right now. Okay? So you can avoid rewriting to avoid using the product rule. So you label the functions u and v in order. The first function u, the second function v. And then you use your label to write the product rule. Okay, so use the label to write the product rule. It's always good to embed the formula in your problem solving process to minimize the chances of making mistakes. Okay, so now you've written down the product rule using the labels that you created, u and v. Now you're going to apply the formula to the terms. Okay, apply the formula or rule to the terms. And in certain cases, you have to simplify your expression. All right, so let's go ahead and take a look at an example. All right, so question number 1. If y is equal to e to the x sine x, then dy dx is equal to. Okay, so let's go ahead and write down the problem. We have y is equal to e to the x sine x. Now what you notice here is there's no manipulation that can be done here, either using trig identities or algebraic manipulation that can result in the avoidance of the product rule. You have to use it. Okay, you can't do term by term differentiation here. So since we're stuck with using the product rule, we're going to proceed to step 2 and label the functions u and v. So the first function is u and the second function is v. So whenever you have a product of two functions and you're looking for the derivative, you're going to have to use the product rule. Okay? Because the operation associating these two functions is a product. Alright, now I'm going to use the label to write down the product rule. So u times v prime is equal to vu prime plus uv prime. Now in some textbooks it's written as uv prime plus vu prime. Since addition commutes, it doesn't really matter the order. Okay? I like expressing it in this format because it's easier to remember the quotient rule, since the quotient rule is vu prime minus uv prime over v squared. So that's why I write it like this. Okay, so we're done with step 2, which is labeling the functions. U is e to the x, v is sine x. We're now going to apply this formula, this rule that we've written, to this function. Okay, that's step number 4. So we're going to have v. I'm going to put the functions that are not to be differentiated in parentheses, sine x, and then the functions to be differentiated, I'll put them in brackets. Okay, so u is e to the x, and we are looking for the derivative of that, plus u e to the x, v prime, v is sine x, I'm looking for the derivative of that, so I put that in bracket also. Okay, so there are two formulas that we're going to be using to finish this product off, two differentiation rules. So let's go ahead and recollect those real quick before we start. You need to remember that the derivative of sine is what? The derivative of sine is cosine x, and that the derivative of the exponential function e to the x is itself. It is its own derivative, which is kind of interesting. Alright, so keep these 2 points in mind. Let's go ahead and start differentiating. Sine x, we bring that down. The derivative of e to the x is just what? E to the x. Plus e to the x, the derivative of sine x is cosine x. Let's rewrite. In order, we have e to the x first, e to the x sine x, plus e to the x cosine x. Okay, so that's the answer, or you can rewrite it by factoring out the e to the x components. You can write it as dy dx equals e to the x sine x plus cosine x. Okay, so whichever way you want to write it, that's the derivative of the function by applying the product rule. Alright, let's take a look at another example. So for question 2, if y is equal to cosine x sine x, then at x equals pi over 6, dy dx is equal to what? Alright, so let's do this. Now, what this problem is asking us to do is to find the derivative at a specific x value. So let's rewrite it in using symbolic notation. Okay, so we're going to restate the problem just to know exactly what we want to do. We want to restate the problem, which is to find dy dx at x equals pi over 6. We want to rewrite this. This is the same thing as simply looking for it's equivalent to finding y prime at pi over 6. Okay? So the derivative at a point is written using symbolic notation only as the y prime at pi over 6. Okay? So this is what we're going to be looking for. Now, anytime you're looking for the derivative at a point, it's a two-in-one problem. Okay? So let's break it up into the two parts so we don't get them confused. Whenever you're looking for the derivative at a point, the first part is the calculus step. Okay? So part 1 is to find the derivative, find the y dx or y prime. And then step 2 is the algebraic process, which involves evaluation. So step 2 is to evaluate y prime at the specified x value. Okay? So anytime you're looking for derivative at a point, do not forget to break the problem up. You do the calculus step first, and then the algebraic step using the order of operations next. Okay? Don't forget that. Now, let's go ahead and rewrite the problem. Y equals cosine x sine x. We can't rewrite this. We have to use the product rule here. So we're just simply going to follow the steps that we outlined earlier. You label the functions u and v. The operation relating them is a product operation, so we're going to be using the product rule. Okay? So step 3 we apply the product rule to the labels that we created. So uv prime is equal to vu prime plus uv prime, the product rule. Okay? If we apply it here, we have u as cosine x, no, v, which is sine x, u prime, let's put that in brackets, so cosine x prime, plus u cosine x times v prime, v is sine x prime. Okay? Now there are two differentiation rules we're going to be using here. Let's go ahead and refresh our memories on that. We went over one before, but I'm just going to put it again. So the differentiation rules that we are going to be using are as follows. The derivative of sine x, remember what that is? From the previous example, the derivative of sine x is cosine x. Now, what's the derivative of cosine x? You have to be careful with this. Why? Because the derivative of cosine x is negative sine x. There's a sign change here. Okay, now let's go ahead and apply these two differentiation rules to the problem. So we have sine x. The derivative of cosine is just as negative sine. So I could put the minus in front here, and then you have minus sine x plus cosine x. The derivative of sine is cosine x. Okay, if we simplify, we have negative sine square x plus cosine square x. Okay, so this is y prime. So what we just did is we did the first part. Let me write it up here. So part 1 is to find y prime. Okay, and we just found y prime. We're done with the calculus step. The next part is to evaluate the derivative at pi over 6. Okay, now this problem can be solved in two ways. You can make use of your identities, your trig identities, or you can just evaluate it directly. Alright, I'll show you both methods. So method 1, so we're doing step 2 now, which is to evaluate the derivative at the specified x value, which is pi over 6. So method 1 is without identities. So if you don't remember your double angle identities, it's fine. You can still solve the problem. It just takes a little bit longer. So without identities, we have y prime equals um, negative sine square x plus cosine square x. So we just evaluate this at pi over 6. What does that mean? You plug in pi over 6 into all the x's. Okay, so we have negative sine square pi over 6 plus cosine square pi over 6. Now what on earth is this? This looks horrible, right? You have the square and a pi over 6. What is going on? So let's rewrite it in such a way that we can clearly see the order of the evaluation procedure. Okay? So the square is the outer function. So what we're going to have is negative sine pi over 6 square. So this, writing it in this format makes the evaluation procedure clear. We see that we're going to evaluate sine pi over 6 first, and then we'll square the resulting answer. Okay? And then cosine square pi over 6, let's write it as cosine pi over 6 square. So the takeaway here is whenever you're dealing with squares of trig functions, when you're differentiating or evaluating, always write it in this format first so you can clearly see the order of composition. Okay? Alright, so sine pi over 6 and cosine pi over 6, you can use your unit circle to solve this. So pi over 6 is 30 degrees on the unit circle. So let's take a look at that real quick. So we are in quadrant 1, and I have my circle coming up. So yeah. Okay. Alright, so for our unit circle, we have 3 points, right? 1, 2, 3 in quadrant 1. The first one, that's 30 degrees, okay? So this angle right here is pi over 6 or 30 degrees. Now what are the coordinates for that one right there? This one, pi over 6. What are the coordinates? So to help us out, we remember that this is a unit circle, so this point here is 1, 0. Okay? So next to 1, if you remember your order of numbers, is root 3 over 2, and next to 0 is 1/2. Alright? And then remember that sine is your y and cosine is your x. Bam. So this helps us to see that sine of pi over 6 is 1/2, so we have negative 1/2. Don't forget we're squaring it. Square plus cosine of pi over 6 is root 3 over 2, so root 3 over 2 square. If you simplify that, you will get negative 1 over 4. You square the top and the bottom. Plus root 3 over 2 square. You square the square roots so they cancel out to give you 3, and then you square 2 and get 4. So don't forget your properties of exponents. Okay, when you're squaring a quotient, you have to square the top and bottom. So you square the numerator and you square the denominator. Alright? Negative 1/4 plus 3/4 is 2 over 4, which simplifies to 1/2. So ladies and gentlemen, there goes your final answer. Okay? So that is, what is it we're looking for? We're looking for y prime of pi over 6. Or we can say dy dx at pi over 6 is equal to 1/2. Now this is how we can do the problem if we don't remember our double angle identities. So let's do the same process using the double angle identities, okay? But if you're satisfied with this method, then you're fine. Okay, so let's take a look at that real quick. Method um, 2 with identities. So all I'm going to do is just rewrite this problem, reverse the order of my of the operation here. So y prime is going to be cosine square x minus sine square x. So you just have to remember that sine square, nope, cosine square theta minus sine square theta is equal to cosine 2 theta. Okay, this is one of your double angle identities. Alright, so let's go ahead and apply it here. So this problem y prime is going to be reduced to cosine 2x. See that? And then y prime evaluated at pi over 6 is going to be cosine 2 times pi over 6. Just input it in there. Okay? If you simplify that, you have cosine 2 goes here 1, 2 goes here 3 times. Cosine pi over 3. Okay? And then if you use your unit circle, this is pi over 3 right here. So we're just going to be using the x coordinate for cosine. The middle angle is pi over 4. Okay? So for pi over 3, remember what the coordinates are. Just switch this around. It's going to be 1/2 comma root 3 over 2. So the x coordinate is a cosine, alright? So cosine pi over 3 is 1 over 2. So this is y prime of pi over 6, which is the same thing as dy dx at pi over 6. Okay? So this is an example of how to use the product rule when you're evaluating the derivative at a point. Okay, so how well did you master the contents of this presentation? Well, to test yourself out, we'd like you to try the following problems. So try these 3 questions. The first one, if y is equal to e to the x cosine x, then dy dx is what? Question 2. If y is equal to x cosine x, find dy dx at x equals 0. Question 3. If y is equal to e to the x cosine x, find d square y dx squared. This is a higher order derivative. Okay, so for question 3, you're just differentiating twice. Alright, so what I'm going to do, or what you're going to do, is pause the video and try out these problems, and then I'll be writing the answers. So if you don't want to see the answers, just pause the video, try out these problems, and then I'll be writing down the answers momentarily. Alright, hopefully you had a chance to try out the problems. These are the answers for problem number 1. dy dx is equal to e to the x cosine x minus e to the x sine x. For problem 2, dy dx at x equals 0, which can be restated as y prime of 0, is equal to 1.